Hello, am I audible to you? Hello Vijay, am I audible? Vijay, am I audible to you? Okay, and are you able to see my screen? Just a minute. Okay, then we will start. It is already 7:06. Yeah. So first of all, I will discuss about the week 8 assignment of last semester. Okay, and then we will discuss about the your doubts. If you have doubt, then we will discuss. And after that, we will discuss some concepts which are taught in the week 8 lectures. Okay, so we will start now. Just okay. I think if you are not able to see my screen, please ask me. Okay, I will change myself. Okay, so this week 8 assignment, first question. Just a minute. Okay, now I think you see clearly. Okay, question number 1. In which of the following case increase in mass is observed during TGA? So when mass will be increased when some oxidation reaction is going on, or means something is adding. So what is adding? Suppose this is metal. Okay, when it reacts with oxygen in presence of heat, it will form some oxides. Okay, we can say MOX. Okay, so it will form some oxides. Let me somebody meeting. Okay, that's why weight gain will be there. Okay, so oxidation, if any oxidation is there, then it will result as a weight gain. Okay, so option is oxidation of ferrous powder in air. Okay, so what will happen here when ferrous powder react with oxygen? Okay, in presence of heat, so it will form Fe2O3 plus Fe3O4 mixture. Okay, means Fe2O3. So if you will find out the oxidation state, so here it will be 6 divided by 2, so plus 3 here. Okay, similarly here 2 oxidation state will be there, plus 2 and plus 3. Okay, so because it is gaining oxygen, so that's why weight will be gained here. Okay, and the answer second will be right. Student, please join on time. Okay, I will, otherwise I have to allow you again and again. Okay, so this is the answer of first question. We will discuss about another option also, why they are incorrect. Okay. So thermal thermal decomposition of copper sulfate. So our question is, in case increase in mass. Okay. So when copper sulfate will be decomposed, will it result in increasing mass? No. Why? When copper sulfate will decompose, as sir already explained, okay, first of all, the 5H2O will be removed. Okay, it will removed in step by step. Okay, initially it will 2, then 2, then 1. Okay, like that. Then you will find pure copper sulfate. Okay, this copper sulfate again decompose here. So here copper sulfate CuSO4 will be decomposed as Cu copper oxide plus SO3 gas. So this SO3 gas will be move up. This arrow sign representing this that this SO3 gas will move out, so that mass loss will be occur here. Okay, and finally it will be copper oxide, again it will be like that. Okay, it is here due to copper oxide will be convert Cu to O. Okay, it is cupric oxide will convert in cuprous oxide. Okay, so these are so in this complete process we are observing that step by step only weight loss is occur. Okay, in this process no weight gain is there, so obviously the option 1 is incorrect. Just a minute. Okay, so option 1 is incorrect. Then question option number C, thermal decomposition of calcium oxalate dot 2H2O. Okay, let me remove it. Okay, so here also, if you I think you know about how calcium oxalate decompose. Here also, first these two water molecules will be removed, then calcium oxalate will be converted in calcium carbonate plus CO carbon monoxide. Okay, then again if you further increase the temperature, then finally calcium carbonate then this will convert calcium carbonate convert in calcium oxide. Okay, plus CO2. So again weight loss. Okay, here it is weight loss due to carbon monoxide, here it is weight loss for carbon dioxide. Okay, and initially it is weight loss due to water molecule. Okay, so this is also wrong answer, because we are here continuously weight loss is occurring. Okay, so this is absolutely incorrect answer. Okay, so I think this option this question is clear. Any doubt regarding this question you can ask. Okay, then question number 2, the number of DTA peak observed during thermal decomposition of calcium oxalate monohydrate in aerial condition. Okay, aerial condition means in presence of oxygen or air. Okay, air obviously air contain oxygen. Okay, so the number of DTA peaks observing calcium oxalate. Okay, so we just discussed in previous question also. Okay, calcium oxalate, first it will due to water loss, dehydration. Okay, second it is due to convert in calcium carbonate plus carbon monoxide, and third calcium carbonate will again convert in calcium oxide plus CO2. Okay, so obviously these three peaks will be occur. Okay, so this will be this product will be removed, okay, from your sample. So due to this three phenomena, three peaks will be observed in calcium oxalate monohydrate dehydration. Okay. So I think this is also clear. Then question number 3. The technique in which temperature difference between the sample material and the reference material is plotted against temperature or time. Okay, delta T. Delta T with reference of means we have two sample, we can say two pen, okay, where we are putting two crucible. In one crucible we are putting reference material, another material we are putting sample, okay, and this whole assembly is getting heated by furnace. Okay, so this is the furnace. So what will happen? Okay, this reference material is inert. Okay, it will just simply what will happen in reference material, when you increase the temperature of reference material will also increase. Okay, so suppose this is for this graph is we are plotting for only reference of material, and it is for furnace temperature and reference material temperature. So what will happen? It should be increased like that. Okay, linear. Why? When furnace temperature will be increased, the reference material temperature also increase. Okay, because it is inert. Nothing will be happen in reference material. Okay, but your sample is sensible toward heat. Okay, so means it will not give you a straight curve. Okay, so suppose let me change the color. Okay, so this colored plot is for suppose okay, this is for reference material. Okay, and now I can say let me remove it. Okay, now it is for sample. So what will happen? Suppose sample temperature, so it will not straight. Okay, initially it will increase it. Okay, after some time, if some melting, glass transition or crystallization something is occur, okay, so what will happen? It will, the temperature will means the temperature which is providing by furnace, or you can say heat is providing by furnace, is consumed in some process. Okay, so here the sample temperature will remain like that. Okay, means what happen here? Furnace temperature is increasing, but your sample temperature is remain constant for some time like that. Again, it will be follow the same path. Okay, but you will get this type of point. Okay, where the heat which is provided by furnace, okay, consume in some process. Okay, so it will be, so what will happen? Suppose again here also I am plotting the graph for reference material. Okay, so reference material will be graph will be like that. Okay, straight line. So here delta T will be there. Okay, temperature difference will be there in the reference material and your sample. So this delta T will be measured. Okay, and it will be plotted against temperature of furnace and time. Okay, so it will be this is the principle of DTA. Okay, so here this is written clearly. Okay, what is written here? That the technique is with temperature difference. Temperature difference means what? In which temperature difference in between sample and the reference material. Okay, when delta T in between what? In between sample material and reference material is plotted against temperature or time, it is known as DTA, which we have explained. Because in TG we plot mass loss with temperature. Okay, DMA is not applicable here. Okay, it is not discussed in this video, so this option is all obviously not considerable. Okay, so only C option is correct. Okay, it is written here. I will just read out. I have already explained, but let me read it. DTA, differential thermal analysis, is a technique in which difference in temperature between sample and reference material is monitored against time or temperature, while the temperature of sample is specified atmosphere. Okay, atmosphere should also be specified. Okay, because atmosphere is mean what, that in your DT analyze which gas you are using. Okay, if you are using oxygen, then plot will be different. If you are using nitrogen, argon, inert gas, then it will be different. Okay, atmosphere is program. In DMA is not discussing, but let me discuss little bit. In DMA, the sample kinetic property are analyzed. Okay, kinetic properties are analyzed by measuring the strain and stress. Okay, so you do. I think some of you are not aware about the strain and stress, so leave it. Okay, that is generated as result of strain and stress varies, oscillate with the time. Okay, applied to the sample, the TG. Okay, the TG, the mass of the, we have already discussed about that. Okay, what is TG? So TG is mass of the sample is monitored against time or temperature. Okay, so these things are already discussed. So question number 4 now. The crucible having the advantage of good thermal conductivity. Okay, good thermal conductivity is what meaning is what. Okay, so material which able to conduct heat easily. Okay, so suppose this is the made of we can say plastic. Okay, suppose this is the plastic, or suppose we can not plastic, suppose it is made of wood. Okay, so this is wood and this is metal. Okay, and if you are heating from this side, okay, suppose you are putting some coil here. Okay, and this coil will hit this side. Okay, first side. So, and here also you are putting one coil and it is hitting from his side. So heat will travel from here to here, and in metal also it will travel from here to here. Okay, so obviously we know that the second end of the metal will heat it first compared to wood. Okay, so the this side second which I marked second here, so the opposite side will heat it fast when the material is made of metal. Okay, not for wood. Okay, that's why wood is bad conductor of heat, whereas metal is good conductor of heat. Okay, or we can say it is a good thermal conductor. Okay, so that's why whenever metal is used, it will good conductivity of thermal. So the question is asking what is the good thermal conductivity. Obviously the crucible which is made of metal will provide good thermal conductivity. Okay, so here this alumina is what, Al2O3. Okay, it is oxide. Silica is also oxide. Okay, Si2O3 and SiO2, sorry. Sapphire crucible, it is also made of alumina. Okay, Al2O3 and some process are there. But this platinum crucible is made of platinum metal. Okay, that's why it is a good thermal conductor. Okay, and if you need good thermal conductivity, then you should go with platinum crucible. Okay, so platinum crucible is right answer. If you require any other explanation, please you can ask. it is already I have explained. Let me. The platinum crucible offer high temperature strength. Okay, it is also provide high temperature strength, which we did not discussed. High melting point. Okay, it is also required. Otherwise, it will be melted, and you will not able to analyze your sample. Platinum offer oxidation resistance. Okay, because some metal oxidize in presence of heat and oxygen. Okay, and make some metal oxide, but this platinum offer oxidation resistance, means it will not oxidize at high temperature. Okay, and corrosion resistance also. Corrosion is also some type of some type of oxidation only. Okay, so it is also resistance of corrosion in acid and melt salted. Okay, because your sample can be acid or base. Okay, it is depend on the property of sample. Okay, so your crucible should be resist of this property. Okay, if your crucible are is reacting with acid or base, okay, then it will react with your sample. Okay, and it will corrode, or it will be you will not able to find exact data. Okay, and it will create error. That's why it should be inert. Okay, that's why platinum is good option. This crucible have advantage of good thermal conductivity. Okay, so thermal conductivity we have already discussed how and why it is good thermal, because it is made of metal. That's why it is a good thermal conductor. Here, question number 5. Match the type of DSC signal given in column A with the process given in column. Okay, so DSC is what? DSC means what? It is calorimetry. Okay, so it will measure the heat which used in different process. Different process means crystallization, glass transition, melting, whatever, sublimation, like it. Okay, so you will be okay. So some this type. Sorry. Okay, so you will able to find this type of peak. Okay, so it will be if it is downward, then it will be endothermic. If it is upward, then it will be exothermic. Endothermic means what? If it is endothermic, means what? That your system is taking energy. Okay, when you are getting endothermic peak, means your system means what? Your sample is taking heat from the system. Okay, when it is exothermic, means your sample is releasing heat. Okay, if your sample is releasing heat, then it will be exothermic. Okay, then now you need to find out which process are endothermic and which process are exothermic. Okay, so exothermic process means we can say so first of all we will discuss about the endothermic. Suppose melting. Okay, so suppose ice is melting in water. Okay, so this process is endothermic. Why it is? Because ice requires some energy to convert in water. Okay, so this is the endothermic process. Similarly, we can say melting. Okay, melting of any metal. Okay, so when your metal will be made, it requires some energy. Okay, so from where it will take energy? It will take energy from the system. Okay, so that's why this endothermic peak will be there. Okay, similarly exothermic reaction, so your sample is releasing heat. Okay, how it will release heat? Okay, suppose it is making crystal. Okay, so when it is making crystal, means it is going to make systematic arrangement. Okay, so initially it was amorphous, it was high energy. Okay, so by crystallization it will release energy. Okay, so when it will release energy, you will find out exothermic. Okay, so in DSC you will get this type of peaks. Let me check somebody. Okay, nobody will get it. Okay, so here I have already explained when you will get endothermic peak and when you will get exothermic peak. Okay, so now we will discuss about the option of this question. large well-defined exotherm. Large well-defined exotherm means you will get very good defined exothermic peak. Okay, so pure okay, when you will get exothermic, when your sample is releasing heat. Okay, so pure crystal melting. Okay, so I have already explained you that when melting is occur, it required energy. Okay, so first option is not right. Then moisture loss. Okay, so moisture loss obviously it requires also some energy, because how moisture will be lost when your sample will take some energy. Okay, and it will be heat up, and due to this heating of your sample, it will release moisture. Okay, so it is also endothermic peak, because your system requires some energy, your sample requires some energy. Third is crystal structure rearrangement. Okay, so this is right answer, because when your crystal structure rearrangement will be there, means initially it has high energy system. Okay, your sample has high energy, but when your crystal will be rearranged, it will release some energy. Okay, and when your sample will release energy, you will find exothermic peak. Okay, so this is the right way to explain. Large well-defined peak exothermic will be there when crystal system rearrangement will be there. Okay, so for X, third is right option. Then large well-defined endotherm. So well-defined endotherm means your system is taking energy. Okay, so endotherm, in pure crystal melting you will get endotherm, and moisture loss also you will get endotherm. But in melting you will get a clear endotherm. Okay, so this is the right option for Y. Okay, so for X it is third, for Y it is first. Okay, and obviously for Z, shallow broad endotherm. Okay, so when moisture loss will be there, you will get broad endotherm. Okay, so second is option for Z. Okay, I think this is clear. Any doubt in this question you can ask. Any doubt regarding this question? Okay. Okay, then next. Just a minute. Okay, so these are the right options we have already discussed. Large well-defined crystal rearrangement, shallow broad endotherm due to moisture loss, and large well-defined endotherm due to pure crystal melting. Question number 6. The nature of DTA peaks observed during thermal decomposition of calcium oxalate monohydrate in aerial condition in presence of CO2R. Okay, now see, in presence of CO2. Okay, so okay, now I will discuss here how calcium oxalate monohydrate will be decomposed. Okay, so calcium monooxalate, we can say C2O4 dot H2O. Okay, so when it will decompose, first mass loss due to what? Due to moisture loss. Then then it is calcium oxalate, then calcium carbonate, then finally calcium nitrate. Okay, so here moisture will be removed, here CO will be removed, and you will find CaCO3. Finally here CO2 will be removed, and here you will find calcium. Okay, so this is the TGA of calcium oxalate. Okay, then if we plot DTA, okay, delta T. DTA means what? Delta T, you are going to plot delta T. Okay, so you will get peak. Okay, so due to moisture loss, we have just discussed, it is a endothermic peak, but broad peak. Okay, then due to carbon monoxide loss, you will get exothermic. Okay, here the atmosphere is in presence of oxygen, you can say. Okay, then here also we will get, sorry, this peak is sharp. Okay, like that. So you will get this exothermic peak here. Okay, this peak is exothermic. Okay, but when you plot, okay, when this reaction is in CO2 environment, where CO2 is there, oxygen is not there. Okay, so CO will burn. Okay, what will happen? It will, in presence of oxygen, it will make CO2. Okay, like that. So it is exothermic reaction. But if carbon monoxide is there and CO2 is there, then it will not react. Okay, so burning is not possible here. So you will get different peak. Okay, this peak will remain same. Here it will, you will get endothermic. Okay, due to this CO removal, but CO will not burn here. Finally you will get this peak at higher temperature little bit. Okay, so this is in presence of CO2 and this is in presence of oxygen. Okay, so here this peak is endothermic. Okay, so did you understand why this peak is exothermic and endothermic here? Any doubt, or did you understand or not? If you have doubt here, you can ask. Okay, so this first plot is TGA. Okay, and these two plots are DTA. Both are DTA. Okay, then what is difference? First is in presence of oxygen and another is in presence of CO2. Okay, so because here carbon, okay, here what happened? Carbon monoxide is releasing by calcium carbonate. Okay, what is the reaction? Calcium carbonate will decompose in calcium oxide plus carbon monoxide here at this point. Okay, so this carbon monoxide will be generated and it will be burned in presence of oxygen. Okay, so this burning is provide energy, so you will get exothermic peak here. Okay, but in presence of carbon dioxide, CO2, the burning of carbon oxide is not possible because oxygen is not present. Okay, so you will get only endothermic peak. Understood? Okay, so exothermic in both case it is wrong. Endothermic in both case. Endothermic in aerial condition, so no, it is also wrong option. Wrong option. It is a exothermic in aerial condition and endothermic in presence of CO. Okay, so this is the right option. Okay, clear? Okay, it is written here. During thermal decomposition of calcium oxalate monohydrate in aerial condition, the obtained due to elimination of CO is exothermic, whereas endothermic in presence of CO2. Because CO burning in presence of CO2 is not exothermic. Okay, so that's why you will get endothermic peak here, and this thing is clear, I think. Question number 7. The number DTA peak observed during thermal decomposition strontium carbonate. Okay, so strontium carbonate. Okay, so obviously there are two peaks. Okay, first peak is due to phase transition and another peak is due to removal of carbon monoxide. Okay, so these are the two peaks you will be able to observe in strontium. Okay. So this is also clear. Sorry, it is CO2, okay, not carbon monoxide. It is CO2. Okay. So during thermal decomposition of strontium carbonate, two peaks are observed in DTA curve due to phase transition and elimination of CO2. Okay, first and second peak. So two peaks will be there. Question number 8. The type of DSC signal produced during the curing reaction. Okay, curing reaction. So do you know what is curing reaction? Do you know what is curing reaction? I think you people are aware about the cement curing. Okay, generally somewhere if you will see some construction work is going on, so whenever plaster or concrete you are making, it generally required some curing time. Okay, so in 24 hours hardness will be generated in cement, but after that also you need some curing time. Okay, where some your cement will solidify. Okay, so this is also a curing reaction. Okay, cement curing. So this type of reaction also occur in your polymer or your some you can say structural composition. Okay, so what will happen? They will make curing. Curing means your in simple language you can say, how you can explain curing. So you can say that your high energy sample is your high energy substance is converting in low energy. Okay, your high energy system is converting in low energy. So how it is possible? How high energy can convert in low energy? By releasing heat. Okay, by releasing heat. Okay, so suppose we already explained electron. So suppose electron is getting excited from here to here. Okay, when so it is high energy for electron, it is low energy. Again, when electron is coming high energy to low energy, so what will happen? It will release energy. Okay, so same thing is here. If your system is high energy and it want to come in lower energy, so it will release heat. Okay, or energy. So whenever energy will be released from your system, obviously it will be exothermic or endothermic peak. If your sample releasing heat, then it will be exothermic or endothermic. Very good, it is exothermic obviously. Okay, so here because due to curing process your sample is releasing heat, so you will get curing, you will get exothermic peak. Okay, so this point is clear. But shallow broad, why it is what is the meaning of this word shallow broad? Because curing process is not very fast, it required a lot of time. Okay, in cement also you can say it required 24-48 hours or sometime some days. Okay, so same thing in a sample or in any compound, the curing time is very high. That's why you will not get sharp peak. Okay, at the place of sharp you will get broad peak like that. Okay, because it required more time. Okay, that's why your this exotherm will be shallow and broad. Okay, understood all this point? Why it is shallow, why it is broad, and why it is exotherm? I think it is clear from this explanation. Okay, any doubt here? No? So it is written here, we will just read it. Curing is a process during which chemical reaction such as polymerization. Okay, polymerization is also same thing. Okay, your monomer. Okay, so these are the monomer. Okay, when they will connect and make polymer, okay, it will release some energy, delta H. Okay, so it is also a curing process. or physical action such as evaporation, okay, takes place, resulting in harder, tougher, or more stable linkage. It gives shallow, broad exothermic. Okay. Then question number 9. Among the following, the incorrect statement is, okay. So here it is given that glass transition is endothermic process is incorrect, but I have doubt in this question because glass transition is also a exothermic process, okay, not endothermic. So I will not discuss this question. Otherwise, all options are incorrect only. During glass transition, sample undergo change in heat capacity. Yes, heat capacity will be changed. So it is correct statement. In glass transition, no formal phase changes occur. Yes, it will only glassy state convert in rubbery state. Okay, or we can say some change in viscosity of your polymer or any material. But phase change is not occur. Okay, so this is also correct statement. Then glass transition can occur when temperature of amorphous solid is increased. Yes, glass transition occur when temperature. So how glass transition will be occur if it is a glassy state? Okay, so when you heat it, okay, heat it by giving energy. When you heat it, it will convert in rubbery state. Okay, so when it is rubbery state, the viscosity will be increased. Okay, and viscosity will be decreased, sorry, not increased. Okay, viscosity will be decreased, and your material will convert in rubbery state. Okay, so that's why this is also correct answer. So this is also correct. Okay, so this is incorrect. Yes, so it is incorrect. It is incorrect, no? Because glass transition is exothermic process. Here it is written in endothermic, so that's why it is incorrect, and we need to find out incorrect only. So this is the right answer. Okay. Then finally, question number 10. Okay, let me read it. The glass liquid transition or glass transition is gradual and reversible transition in amorphous material or in amorphous region within semi-crystalline material, or amorphous region in semi-crystalline material. So what is meaning of semi-crystalline? Okay, suppose it is a polymer. Okay, so somewhere it is, the chain is very well arranged, but somewhere it is like that. Okay, again somewhere it is very well arranged, then it is amorphous. Okay, so it is known as a semi-crystalline material. Why it is semi-crystalline? Because somewhere it is very well arranged and it is in crystalline, but other portion is amorphous. Okay, so what will happen when you increase temperature? This crystalline part will be converted in amorphous. Okay, by gaining energy, this polymer chain will try to open up. Okay, and when the polymer chain will open, the amorphous region will also increase. Okay, so it is only written here. So let me remove it. Okay, so from hard to relatively brittle gaseous state into viscous or rubbery state. Okay, so this brittle state is converting in rubbery state as temperature increase. Okay, so when you increase temperature, this phenomena will be happen. During glass transition, sample undergoes change in heat capacity. The glass transition, no formal change occur. Glass transition is an exothermic process. Yes, it is written here clearly. It is an exothermic process which result in a peak of DSCC. Glass transition can occur when temperature of amorphous solid is increased. Okay, so glass transition, when glass transition will be occur. Glass transition is similarly melting. Okay, PM and TG. So for metal only we discuss about the melting point, but if it is polymer, so it will be, initially it will be glass transition temperature. Okay, initially it will be glass transition temperature. Suppose any polymer which has -33, suppose it is ethyl vinyl acetate, it is a polymer. Okay, so this EVA has 33 degrees centigrade TG, then it is melting temperature is around 55. Okay, so this is the temperature plus 55. Okay, so you can say that initially your glassy state convert in rubbery state. Then if you further heat your rubbery state, then it will convert in then it will melt out. Okay, so these are the things. Okay. Let me check, is somebody waiting? No. Okay, so this is all about question number 9. Then question number 10. It is also very simple question. We have already explained about that. During the thermogravimetric analysis of copper sulfate, in which step two water okay, during the thermogravimetric analysis of copper sulfate 5H2O, in which step two water molecules are released simultaneously. Okay, so copper sulfate has 5H2O, and when you heat your sample, all 5 molecules will not remove together. Okay, they will remove step by step. Initially 2, then 2, then 1, like that. Okay, so here 2H2O will be released. Here also 2H2O will be released, and here 1H2O molecule will be released. And here you will get what? Copper sulfate. Okay, here it was copper sulfate dot 5H2O. Okay, so step by step all water molecule released from the copper sulfate. Okay, if you further it, then it will remove SO3 like that, and it will convert it outside, and then again it will be where it will be converted. Okay, so these are all the process we have already discussed. But according to answer this question, step 1 and step 2. Okay, so 2 water molecule released simultaneously. So in first step 2 molecule released, and again second step 2 molecule will be released. Okay, this is the first step, and it is the second step. That's why our option 1 is correct. Okay. Student, please join on time. Okay, why you are joining after 1 hour where all discussion is completed? Okay. So okay, so it is all about the assignment, 8th assignment of the last semester. Okay, it will help you. It will help you to solve assignment question of current week. Okay. So here I am going to stop, and I want to ask question from your side. If you have any doubt in this week videos, you can ask. Otherwise, I will give some. Otherwise, I will explain some concepts which are important for you. Okay. First of all, if you have any doubt, you can ask. Yes. 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 So, Miss, we discussed curing process. Am I right? Okay. Curing process, and one more example I can take, melting. Okay. So melting, we know that a particular temperature melting will be occur. Okay. So you will get sharp peak because at particular temperature delta T will be difference. Okay. Because we know but in curing process it requires more time to complete the reaction. That's why you will get peak like that. Clear? Yeah. Yes, obviously. If crystal, ha, yes, broad peak like that. Okay, yeah, if it is like that, because yeah, this case is for metal. You can say metal. Okay, but this case for crystalline material, but not metal. Then yeah, then the peak will be broader. Right. Okay, thank you. Any other doubt? Other student? Okay, so we have one more over. If you have any doubt, you can ask. Otherwise, I will just discuss some concepts which will help you to understand these quick lectures. Okay, so this is okay. So as we have already discussed, type of thermal analysis. TG we have discussed previous week, and DT and DSC we discussed in this week. Okay. So full form of these techniques are already discussed. These are differential thermal analysis and differential scanning calorimeter. So what is difference here? In DTA we measure delta T. Okay. Temperature difference between reference material and your sample. But in calorimetry you measure heat flow. Okay. Here we will measure heat flow with temperature or time. Okay, so here you will get peaks. Okay, so this peak is responsible, means how much energy your sample is taking, or in case of exothermic peak, how much energy your sample is leaving. Okay, so by measuring this area of this peak, you can measure heat. Okay, how much heat your sample is taking, and according to that you can quantify that which sample is there and which phenomena is there. Okay, what is occurring, it is crystallization, melting, glass transition, whatever. Okay, so you can correlate these things. So first of all we will discuss about differential thermal analysis. Okay, so I will not discuss about this. Okay, from here we will discuss definition. DTA is a technique in which the temperature between, okay, temperature between sample and thermally inert reference. Okay, you cannot take any reference material, it should be thermally inert. Okay, why it should be thermally inert? Otherwise it will take heat. Okay, if it will take heat, then you will not able to compare with your sample. Okay, so your reference should be thermally inert. Okay, it continuously recorded as a function of temperature and time. Okay, so what we are measuring? We are measuring delta T. Okay, and why delta T will be occur? Because your reference is inert, but your sample is take energy at a particular temperature. Okay, so at that time the temperature will be difference. Okay, in a sample and reference. So this delta T you will be measured and you will plot against temperature and time, and you will get some peaks, and then you will correlate this peak with your sample. Okay. So in DTA, both test sample and inert reference material control heating or cooling program. Okay, control heating means what? You will heat your sample in fixed rate like 10 degree centigrade per minute. So what is meaning of this thing? Means you are increasing your temperature 10 degree per minute. Okay, so after 1 minute your temperature will be 10 minutes, after 2 minutes temperature will be 20 degree centigrade, after 3 minutes it will be 30 degree, like that. Okay, so your temperature will be increased like that in uniform fashion. Okay, that's why it is known as a control heating. And same control cooling also. Suppose you are cooling at the same rate like 10 degree per minute, so it will reduce your temperature 10 degree per minute. Okay, in zero temperature difference between sample and reference material, sample do not any chemical physical change. Okay, when your delta T is 0, means what? Your reference material is not taking any heat, we know, but your sample is also not taking any heat. That's why delta T is 0. Means we can say the temperature of reference and your sample is same. Okay, so if temperature is same, means whatever heat you are providing, it is able to heat reference and it is able to heat your sample also. But if any reaction will be occurring in sample, then only this heat will be consumed there. Otherwise, this heat will be responsible for only increasing of temperature. Okay, so if delta T is 0, then you can say yes, there is no reaction in sample, it is behaving as a reference material. Okay, whenever if you further increase the temperature, at some point your sample will absorb the energy. Okay, and at that point delta T will be not equal to 0. Okay, because now your sample is taking some heat, but here again your reference is not taking any heat, but your sample is taking heat. Okay, so this heat will be taken by sample due to some process. That's why the temperature difference will be occur. Okay, so this thing will be mentioned. Okay, this is all only written here. If any reaction takes place, temperature difference delta T will be occur between sample reaction. Okay, when it will be there, if any reaction takes place. Okay, it is written reaction means it is not chemical reaction. It is only, you can say, some change. It can be either physical, chemical, whatever. Okay, so at that time delta T will be different. Now what is the DTA principle? Okay, so DTA principle we have already discussed, that delta T will be plot against temperature. Sometime it will be time also. Okay, but here it is plotted with temperature. Okay, so if delta T is 0, so here suppose it is 0. Okay, then you will get straight line like that. Okay, but when your sample is taking heat, when your sample is releasing heat, then you will get exotherm. Similarly, when your sample is taking heat, then it will get endotherm like that. Okay, so this type of peaks you will be able to find. Okay, and it is due to temperature difference. Okay, so differential thermal analysis is a technique in which the temperature of the substance under investigation is compared with the temperature of a thermally inert material. Okay, I think it is clear. Any doubt up to here? Okay, I think somebody is, yes, okay, good. Okay, then differential thermal analysis. Okay, so what are the parts of your instrument, DTA analysis instrument, you can say. So sample holder. Okay, so sample and reference cell. Okay, so to hold your sample and to hold your reference material, so there is cells. Two cells are there. Okay, then sensors. So why we require sensor? We require sensor to measure temperature. Okay, one sensor is here, one sensor is here. It is also known as thermocouple. Okay, thermocouple means it is made of two metals. Okay, that's it is known as thermocouples. Okay, and they will how thermocouple work, I will give little bit about the little bit knowledge about thermocouple. So when temperature difference will be there, they will provide some electricity. Okay, and you will able to measure this electricity in the form of temperature change. Okay, so here suppose two thermocouple is there. This is TC1 and it is a TC2, thermocouple 1 and thermocouple 2. Okay, so suppose this is the reference material and this is the sample material. Okay, and here you are putting some instrument which will measure the difference delta T. Okay, you can measure delta T, na? Because Suppose initially you are heating from here. This is the furnace. Okay, this is the furnace. Okay, so when you heating reference and sample, okay, they are means heated by same furnace. Okay, so same rate, they both reference and sample are heating by the furnace by the same rate. But if some reaction, whenever some reaction will be occur in sample, delta T will be difference. Okay, you will get some delta T. Okay, so because heat will consume in reaction of sample, but in reference no reaction will be happen. Okay, so whatever heat you are providing, it will be consumed on in only increasing of the temperature. Okay, so if you plot the reference, this is the reference material, but you will get this type of plot. Okay, this type of plot you will get for sample. Okay, where you will get, it is the furnace temperature, we can say, or temperature, simply we can say temperature. Okay, and this is the temperature for sample. Okay, okay, so this is the temperature of means you can say your atmosphere, inner atmosphere. Okay, but and this is the temperature of sample. Okay, so temperature of sample we cannot say, we can say how much temperature is increasing. Okay, you can say it is temperature in. Okay, and what is the temperature of your sample and reference? So this T is for, we write only temperature. Okay, so this temperature for your reference and sample. Okay, so your reference temperature will be increased in straight line. Okay, so we can put difference color. Okay, you can say this green line, straight green line. Okay, straight green line. But for reference material, you will get peak like that. Okay, so this is the reference material. Sorry, I am just this is the reference. This is the sample. Where you are getting peak, it is for sample, and where you are getting straight line, it is for reference. Okay, so this green line is for reference, and this where you are getting this slope, this is the for sample. Okay, then this is the DTA instrument we have just discussed. Okay, this is the furnace. Okay, and your sample and reference is covered by furnace, and it will be heated up. Okay, so these are the two thermocouples, you can say, and the difference in temperature will be measured. Okay, and this will be amplified, whatever, and finally you will get result. Okay, so that where you are getting delta T, at which temperature you are getting delta T. According to that, you can characterize phenomena, that what is going on. It is melting, sublimation, crystallization, whatever. So what are the advantages of differential thermal analysis? So advantages are, instrument can be used at very high temperature. Okay, in DTA, instrument can be used very high temperature. Instrument are highly sensitive, flexible, and crucible volume. Okay, so crucible volume you can change, okay, according to your sample weight and your sample volume. Characteristic transition or reaction temperature can be accurately determined. Okay, characteristic transition means this is only transition, melting, okay, or glass transition. So this type of transition you can measure correctly. Disadvantage is uncertainty of heat of fusion, transition, or reaction estimation is 20 to 50%. Okay, so in this phenomena you will get 20 to 50% of error. Okay, uncertainty. Okay, so uncertainty you will get. So this is the disadvantage of this technique. So application of DTA. It is already well discussed that it is used for qualitative and quantitative analysis. Then polymer material. Okay, so this thermal analysis is, you can say, key for polymer. Okay, to characterize polymer, this thermal analysis is very important. Okay, compared to inorganic and organic material. Organic means polymer is an organic material only because it has carbon. Okay, so compared to inorganic material, organic material has higher advantage of thermal analysis, where polymer section is very much known for the characterization by thermal analysis. Okay, so DTA useful for characterization of polymeric material in light and identification of thermal, physical, thermochemical, thermomechanical and thermoelastic change in touch. Then measurement of crystalline. Okay, so it can be also measure that how much your material is crystalline. Okay, by the measuring the area of peak. Okay, so this peak will give you heat. Okay, that how much heat is consumed to crystalline. Okay, so according to that you can calculate that your material is, how much your material is crystalline. Okay, if your material is, if it is taking more heat, then your material will be more crystalline. Like that you can correlate. Okay, so measurement of the mass fraction of crystalline material in semi-crystalline polymer. Then analysis of biological material. Okay, biological material, pharmaceutical material. Here also DTA are used. Okay, it is used also for archaeological material. Okay, now we are going to discuss about differential scanning calorimetry. Okay, so differential scanning calorimetry, what is this? Okay, so I will not discuss about the history and whatever. Principle. Okay, we will discuss about the principle. So in DSC, the heat flow is measured and plotted against temperature. Heat flow. Here, what we are plotting? Heat flow. In previous technique, we are plotting delta T. Okay, this is only change in DT and DSC. Okay, so in DSC, the heat flow is measured and plotted against temperature of furnace or time to get thermogram. This is the basis of differential scanning calorimeter. Okay. The deviation observed above the base line is called exothermic transition, and below is endothermic transition. Okay, so it is similar within DTA. The area under the peak directly proportional to the heat evolved or absorbed by the reaction. Okay, so I just explained you, if area is more, then you can say that more energy is consumed. Okay, and if it is exothermic peak, then you can say the more energy is evolved by your sample. And the and the height of curve is directly proportional to rate of reaction. Okay, so in simple language we can say the area is the area of peak is responsible how much heat it is how much heat it is taking or evolving by sample, and the height of peak means how much, what is the rate of reaction, means if rate of reaction is high, then the height of peak will be higher. Right. Okay. So this is the typical DSC curve. Okay. So initially this is the temperature. This axis is representing temperature and the y-axis is representing heat flow. Okay, so here you can set Tg. So Tg means your system is releasing some heat, so you are getting some so this peak is increasing. Then here it is crystallization. So crystallization means what? Your system is crystallized. So whenever your system is crystallized, Whenever a sample is crystallized, it will release energy. Okay, so when it will release energy, okay, so you will get this type of peak. Okay, then it is melting, so heat flow will be up. Okay, heat here means what? The heat flow means heat is flowing in your system. That's why you are getting peak up. Okay, here is crystallization. Crystallization means what? The heat is means releasing. Okay, so this type of peak you will get. Okay, so this is a typical DSC curve. Then there are two type of DSC, heat flux DSC. So in heat flux DSC, what will happen? You are providing heat flux. Okay, so it will be more clear from the diagram. Yeah. Okay, so see, this is the arrangement of heat flux DSC. So this is the you can say these are the two things. Okay, it is for reference. Okay, this pen is for reference and this pen is for sample. Okay, so this whole system is closed in this heating block, or you can say furnace. Okay, so you are providing same heat flux. You are providing same heat flux for reference and system. What is meaning of this thing? Means what? Whatever you are heating this block, you are providing same heat for reference and sample. Okay, so it is known as heat flux DSC. Okay, you are providing same heat. Okay, but when it is another type of DSC, which is known as power compensation DSC. So what is happening here? This is the sample pen and this is the reference pen. Okay, so what will happen when you are heating it? Okay, so when you are heating it, what will happen? Your sample, some reaction will be happen here. Okay, and due to some reaction, here temperature will be down or up. Okay, it is depend on your reaction. Okay, either it will be exothermic or endothermic. So when your temperature will be rise or up, here you will get, at that point you will get some signal, and here it is instructed that delta T should be 0. Delta T means what? This temperature and this temperature remains same. If the temperature is changed, then it will provide extra heat here. Okay, so what is meaning of it? It is power compensation. So you are giving heat here only. Okay, or why you are giving heat? Because your sample is consuming some heat, but your reference material is not. So whatever heat is consuming, you are providing from outside. Okay, so this only the point which we need to discuss is differential thermal power is supplied. Differential thermal power is supplied to the heater to maintain the temperature of the sample and reference at the program. Okay, so what we are maintaining? We are maintaining sample and reference same temperature. Okay, or we can say delta T should be 0. How it will be 0? If some reaction is occurring in sample and it is taking heat and temperature is going down, so you will provide extra temperature or extra energy, like that. Okay, I think it is clear to you. Then similarly, what are the application of DSC? So it is a protein stability and folding. Okay, even you can find out protein stability and folding. Okay, folding means it requires very minute energy change, but this are also you can measure by DSC. Okay, so it is very sensitive. Liquid biopharmaceutical formulation. Okay, in biopharma because mainly drugs are made of organic material. Okay, it is made of organic material, and this DSC is very good for organic material. Then it is for process development. Okay, so by process development means you can say where crystallization is occur, where melting is occur. Okay, so this phenomena you can identify very well by DSC. Okay, so after that you can measure process. Okay, so suppose you are going to make something from X to Y. Okay, but you know that which peak will be occur at which place. Okay, so according to that you can measure, you can develop your process. So similarly, protein engineering you can say rank, order binding, antibody domain study, characterization of membrane, lipid, nucleate. Okay, whatever it is written here, you can find out, you can read it. Okay, nothing to explain more. Okay, okay. So this is polymer is separately explained here. Okay, because this DSC technique is very useful for polymer. Okay, that's why it is explained separately here. Composition of polymer is determined. Okay, by DSC you can identify the composition of polymer, melting point, glass transition. It is not last transition, it is glass transition. Okay, glass transition temperature can be determined. This can show the polymer degradation by lowering the melting point. Okay, then molecular weight can be determined. Percentage crystallinity also can be determined. Okay, whatever heat it is taking, you can explain. By this you can explain the percent crystallinity. Then thermal degradation and impurities. Okay, if impurity is there, obviously the peak you will get different delta H. Okay, because if it is pure sample, delta H will be different because it will be decrease or increase, and it is depend on impurity. Okay, liquid crystal. Liquid crystal, it is your case. Okay, so these are the reference, and this is the end of this session. Okay, so I have discussed about this thing. Okay, let me discuss some more concept which I think I should discuss here. One more thing I need to discuss here. Okay, so suppose you are going to discuss about heating rate. Okay, now we are not discussing about DSC. Okay, we just discussing about TGA, where one more point I have to discuss, which is weight heating rate. Okay, what is the how heating rate influence TGA? Somebody okay, how heating rate will be influence TGA curve. Okay, so just a minute. Okay, so suppose I am making this TGA curve. Okay, so this is the weight loss, and this you can say first we will discuss about time. Okay, so if heating rate is higher, okay, if heating rate is higher, then what will happen in short time? Okay, in short time your polymer will be decomposed like that. Okay, suppose it is 10 minutes, this is 20 minutes. Okay, so you can say 10 minutes it is consumed, weight loss occur very waste loss rate was very high. Okay, and it is decomposed like that, whatever. And this here suppose this heating rate is, I will tell you, suppose it is a 50 degree centigrade per minute. Okay, now suppose I am reducing the heating rate at 10 degree per centigrade, then what will happen? Okay, so weight loss will be occur Okay, very slowly, like that. Okay, I am not able to draw very clearly, but you can understand like that. Okay, so this heating rate is at 10 degrees centigrade per minute. Okay, so what you are understanding by this way, that when your heating rate was very high, the weight loss is also very high, and your sample is decomposed in very short time. But when your heating rate is very when your heating rate is low, 10 degree per minute, it take high time to decompose. Suppose it is 60 minutes here. Okay, so initially it take only 20 minutes at high heating rate, but at 60 degree. But when temperature increase, it took more time to decompose. Okay, so this is all about how heating rate will change the time of decomposition, and how your thermograph also will be changed. Okay, then we can also discuss same thing we can discuss, and we can plot with temperature also. Here we plot with time. Now I am going to plot with, it is weight loss with temperature. Okay, now heating rate is different. First it is a 50 degree centigrade only. Okay, so first so what will happen, weight loss will be occur like that. Okay, means what is meaning of that, that if your heating rate is higher, weight loss will be occur at higher temperature. If your heating rate is higher, weight loss will be occur at higher temperature. Okay, but if it is low, then I need to change the color. So what will happen, weight loss will be occur like that. Okay, so this is suppose 10 degree per minute. This heating rate is same. So suppose you are plotting one, you are going to measure here. Suppose it is 100, it is 100 degree centigrade. Okay, and you are going to plot a straight line. Okay, suppose you are going to plot straight line. Okay, so you will able to find out that weight loss at 100 degree centigrade, weight loss of this material, this heating rate at 10 degree centigrade means it is suppose it is around 40%, and it is suppose 10%. Okay, only minor, it is not you are not able to see, but you can say that it is a 10% only. Okay, here it is 10% only, but here it is 40%. Okay, so but at 100 degree temperature only, material is 40% decomposed, but at higher temperature, at 100 degree, at higher heating rate, at 100 degree temperature, only 10% is consumed. Okay, that's why it is also, it should be also optimized. Okay, and you need to fix heating rate where you will able to find out sharp decreasing like that. Okay, so you will be able to, you need to find out this type of sharp decreasing of your sample. Okay, so this is the effect of heating rate inversion. Okay, then some different type of TJ curve are there, and you should able to identify. Okay, first simpler, this type of curve is occur when weight loss is occur. Then this type of TJ plot you will find. Sometime you will also find this type of plot. Okay, it is due to weight gain. Okay, this plot is due to weight gain. This type of plot is also explained. Okay, correction needed. Okay, so you can say here nitrogen and here oxygen. So what will happen? Whatever sample you are taking in nitrogen atmosphere, it is not decomposing, and nothing is going happen because it is inert atmosphere. Okay, so nothing is occurring in your sample. But at the instant you are changing the atmosphere. Okay, you are changing the atmosphere gas by oxygen. Sudden decrease in your sample loss will be in sample. Okay, so this TGA thermogram is representing this thing. Okay, multi-step decomposition we have already discussed, like that, multi-step. Okay. Then some type it will be also like that. Okay. Some type you will also able to find this type of thermogram. Okay, where initially it will gain some weight. After that it will be decomposed drastically. Okay, it is also known as a explosive decomposition. Okay, so this concept also I need to explain you. And let me see whatever is remaining. Okay, so we discussed about that DSC can be used for process development also. Okay, so similarly, suppose it is a zinc. Just a minute. Yes. So suppose it is a zinc sulfide. Okay, when you are heating it at 950 degrees centigrade. Okay, so in presence of oxygen. Okay, so what will happen? This zinc sulfide will react with oxygen, and it will convert in zinc oxide plus SO2 gas. Okay, so it will take energy and it will convert zinc oxide in SO2. Okay, so this SO2 will be released, and so if you want to find out that at which temperature this reaction will be occur and how much enthalpy it required, okay, to complete this reaction. So for this purpose we use DSC for this type of sample. Okay, and according to that we develop optimized process where we need minimum energy and we can fulfill our purpose. Okay, so this conversion 950 degree centigrade, suppose energy required, I can do this reaction at 1000 degree centigrade also, na? But what I am doing here, I am losing 50 degree centigrade. Okay, wasting. Okay, so I am wasting energy here. So this type of optimization can be occur by calculating enthalpy of the reactions of different process. Okay. Okay, then some more concepts. So we have already discussed there's a large well-defined endotherm. Okay, in DTA, large well-defined endotherm, which is it is due to pure crystal melting, liquid crystal, dehydrate, hydrate loss means water loss, and stress relaxation. Okay, these are the phenomena where you will get sharp peak, sharp endotherm. Okay, because these all things are required energy. Okay, then shallow endotherm, okay, which are moisture loss, because moisture loss need energy, but it is need energy for longer time. Okay, that's why you will get shallow broad endotherm. Then also residual solvent and monomer losses. Sublimation, sublimation also not you will not get very sharp peak like melting, you will get broad peak. Okay, then exotherm. So when you will get exotherm in the crystallization, degradation of highly unstable material. Okay, if you are getting degraded material, then you will get exotherm. Then crystal structure rearrangement. Whenever crystal structure rearrangement will be there, it will turn in lower energy crystal structure and it will release energy. Okay, so these are the systems where you will able to find exotherm and endotherm. So we discussed that peak area. Okay, peak area of this curve is related to is proportional to delta H means heat is taken by your sample. Okay, for this particular transition. Okay, how much it is heat is taking, and it is also proportional to m, mass of sample. Okay, so this to remove this proportional sign, you need to put some constant. Okay, so it will be minus k and g. Here we are putting two parameters. So k is a constant where g is your calibration factor of your instrument. Okay, so finally the peak area will be you can find out the peak area by this equation. Okay, this is only single equation which is stored in this period. Okay, so by that note, I have done with this week assignment and this week concepts. Okay, which are taught by sir. Okay, so I am going to end my thing here. So if you have any doubt regarding lectures taught by sir or in ongoing lecture and whatever concept and whatever assignment I have solved here, if you have any doubt, you can ask. Okay.